If you remember what I said in Lecture 4.1, Introduction to Mechanics, I mentioned that there were generally two ways to approach problems on dynamics. That is through the analysis of force or analysis of energy. We will be discussing the latter in this lecture series. We will start by connecting the notion of force, which we just learned previously, to the notion of work and eventually kinetic energy, which we will learn in this lecture. So let's get back to our familiar illustration of man pushing the crate. At one moment t0, a man applies some force F to a crate which is already moving forward at speed v0. At later time tf, the crate has been displaced forward by a delta d, and now moving at speed vf. For the sake of illustration, the crate is drawn to stop in this slide, but you can think of this diagram as a snippet of the motion. In actuality, the crate will have to continue on moving. Since force causes acceleration, and the direction of the initial motion is the same as the direction of the applied force, we know that Vf has to be larger than V0. Keep this in mind for now, as we will come back to this again at later slides. Now in everyday sense, this feat definitely requires a certain amount of work from the man. How much work does the man have to apply to push this crate in such manner over the displacement of delta d? Or perhaps before even we talk on how much, what is work in physics? Well, however you understand about work from daily conversation, don't mix it up with how physics understands work. Physics understands that work is done on an object when a force exerted on an object displaces the object along the direction of the force. Mathematically, it is defined as such. In light of this mathematical equation which defines what work is, allow me to repeat that slowly, emphasizing the keywords involved. I said, work is done on an object when a force displaces the object along the direction of the force. Let's analyze them one by one. Work is denoted by capital W. Note that it is the same letter used to denote weight. This is the convention used in many literatures. I did mention to you before that there are so many physical quantities that we have to use both Roman and Greek alphabets, small and capital case, didn't I? Some of them are used repeatedly for different quantities. You should be able to distinguish W for work and W for weight from its context. The SI unit of work is given by the SI unit of force multiplied by the SI unit of displacement, which is Newton times meter or Newton meter. Newton meter can further be written as joule, named after James Prescott Joule, a 19th century physicist who studied heat and its relationship to mechanical work. Some of you might have recalled that joule is also the SI unit of energy. Indeed, you can think of work as a form of energy. We will come back to this at the later part of this video. Force, well, we just learned about force, didn't we? The only thing I would like to point out here is that if you remember the convention of denoting a vector, when it is written as a regular font, not in bold, neither is it accompanied by an arrow on top, we are referring to the magnitude of the vector. Hence, in this equation, we are only concerned with the scalar or magnitude component of the force. Similarly, delta d refers only to the magnitude of the displacement vector. So if we now examine the equation as a whole, F times delta d will result in a quantity devoid of direction in any physical sense. That is to say, a scalar quantity. Indeed, work is a scalar quantity. That is what I would like to say. More interestingly, consider this case. Say you're attempting to push a big super heavy solid marble boulder on a relatively rough surface. Obviously, no matter how much force you apply to the boulder, it is just simply impossible to move. Now in everyday sense, you might think you have done work. After all, you are sweating profusely in the process. But no, unfortunately, as far as the rock is concerned, there is no work done on it because the force does not cause any displacement. Of course, what actually happens is that your applied force is cancelled out by the static friction force between the rock and the ground. The net force acting on the rock is thus 0. F is 0, hence W is 0, hence no work is done. Sorry. Finally, the most intriguing part of this equation is the cosine theta component. Here theta refers to the angle between the direction of the applied force and the displacement. So for instance, in this slide, the force is applied toward the right. The crate is also displaced to the right. Thus, both the force and the displacement are pointing in the same direction. The angle between the force and the direction is 0 degree. If theta is 0, cosine theta is 1. Hence, The work in this particular case is simply given by F times delta D. Now that's pretty straightforward. But if the direction of the applied force is not the same as the direction of the displacement, such as in this example we encountered previously, notice that the displacement is no longer aligned with the applied force. The crate is displaced horizontally to the left, but the applied force is making an angle 30 degrees with horizontal. If you are then asked to compute the work done by this force, there are two ways to approach the problem. First, we follow strictly the formula. F times delta D times cosine of the angle between the force and the displacement. This angle is 30 degrees, hence it becomes F times delta D times cosine 30 degrees, and you can compute the rest. The alternative way is by identifying the amount of force which contributes to the displacement. Recall from lecture 5.2 how this sort of diagonal force can be resolved to its component along the horizontal and vertical. Only the horizontal component of the force, which is aligned to the displacement, contributes to the work. The vertical component of the force, Fy, does no work to the crate because it does not contribute to the displacement of the crate. And since this horizontal component of the force, which we just call Fx for convenience, is already aligned to the displacement, theta is 0 and cosine theta is 1. Hence, W is equal to Fx times delta D. But what is Fx? Fx is equal to F cosine 30 degrees. You should have been familiar with resolving force along x and y using cosine and sine by now. Hence, it becomes F cosine 30 times delta D, and at the end of the day, we end up with the same result as one from the first approach. Of course we should, as both approaches have to be consistent with each other. So do you get how the last component in the equation plays its role? Another extreme case is when the applied force is opposing the displacement, such as the braking force that the man exerts on the crate. The force is applied to the right, but from the moment the force is applied, when the crate is in contact with the man, until it stops, the crate has been displaced to the left. The force and the displacement differs 180 degrees in direction. Now cosine 180 degrees is minus 1. Hence, the work done on the crate is negative F times delta D. Notice from this example that work could be negative too. Like in any scalar quantities, positive negative sign is not used to describe direction. It doesn't make sense talking about work to the left or work goes up. Rather, positive negative is used to describe an increase or decrease in something. In the context of work, what is this thing? Well, hang on for the moment, we are getting there. After we establish the definition of work in terms of force, we are now ready to establish the connection between work and energy, and thereby the connection between force and energy. We come back to our very first illustration of the man pushing the crate. We start from the defining equation of work itself. W is equal to F times delta D. Now let's assume that we are only dealing with forces which are already aligned to the displacement. They could be directed along or opposite to the displacement. So we are able to drop the cosine theta factor from the equation. Cosine theta is 1 if the force is directed along the displacement, as shown in this slide, and it is negative 1 if opposing the displacement. We look at the former case first. Notice that if we replace F with ma because of Newton's second law, we have m times a times delta d. This becomes a situation pertaining to accelerated motion model. The crate is accelerated because of the applied force, and while it is being accelerated, it covers delta d. We can rewrite a times delta d in terms of final velocity Vf and initial velocity V0. Review back lecture 4.3 if you forget. Now, if we define 1/2 times mass times the square of the speed as kinetic energy, denoted with capital K, we arrive at the conclusion that work done on an object is signified by the change in its kinetic energy. Kinetic energy is a form of energy. As the term kinetic suggests, it is an energy that an object possesses because of its motion. It must be in motion to possess kinetic energy, and vice versa, kinetic energy implies the object is in motion. From the equation, if V is 0, then K will be 0 as well. This concept that work done on the object is equal to the change in the object's kinetic energy is what known as work energy theorem. When the work is positive, that means the change in kinetic energy delta K is also positive. That means final kinetic energy of the object is higher than its initial kinetic energy. Because kinetic energy is proportional to the speed square of the object, that means final speed of the object is higher than its initial speed. In the language of kinematics, we say that the object is accelerating. Is this consistent with what we learned from Newton's law? Well, it is. Remember, for work to be positive, the force, or at least one component of the force, must be directed along the displacement. That means the force is directed in the same direction as the motion of the object. The force reinforces the motion, and the object should accelerate. Vice versa, when work is negative, remember a couple of minutes ago I just mentioned that work could either be positive or negative, but this positive-negative does not refer to direction. Work is a scalar quantity, it does not carry any direction. Now we learned that negative work implies a decrease in kinetic energy. When kinetic energy decreases, the object is decelerating. This is also consistent with Newton's law. For work to be negative, the force must be opposing the motion of the object. Remember, that man was trying to stop the crate. He applied a force which opposed the displacement of the crate. That was a braking force, and the object was decelerating. In conclusion, this lecture discusses how work is computed from force, and how work introduces the notion of kinetic energy. Concepts and equations from kinematics and dynamics are mixed together. This is getting exciting, isn't it?